Hello everyone and welcome. I'm thrilled to kick off our next CATIA Systems Masterclass. Today, we are diving into the crucial topic, accelerating digital engineering with MBSE and virtual twin about robotic arm. Our speaker today is MBSE Ecosystem Director Saulis Pavalkis.
Hello,
During this
Gita.
masterclass, During this masterclass, Solus will present the best-in-class example designed to demonstrate the practical impact of systems engineering with SysML on the virtual twin across the entire product lifecycle. During and after the session, you will be able to ask questions, and our speaker will spend some time to answer them. So we are ready to start. Solus, the stage is yours.
Hello, Gitana. Hello, everyone. Thank you for having me here, and thank you for organizing this event. So today we'll talk about digital engineering, model-based digital engineering, and virtual twin in context of robotic arm, but that could be any other system. So here we see a short demonstration. Here we see an executive business area. This robotic arm is presented, and as you can see here, it is actually connecting multiple disciplines together, not only to specify how that system works, but also how it was designed. So now we'll go step by step and explain this whole project and what you can get from it. So first of all, motivation. So in COSI, in the vision 2035 specifies that system engineering is not only for system engineers. So we need to deliver on that vision and explain how system engineering affects the rest of the engineering and final product. Also, our clients like Lockheed Martin for years were saying that we practice system engineering as next level in order to have better products, and that return of investment is actually how we get those better products faster, better, right? And also others are talking about what are the deliverables of system engineering. Sometimes it's hard to know because you are not directly producing the final product, but you are delivering views, models for the disciplines like electrical, mechanical, software, in order just write ones as requirements in order to build again better products. So that's what is scope of this project, to explain what can be that path, through the engineering life cycle, delivering right and connecting disciplines in a tight way. Here, as you can see in this project, we are covering requirements management, system architecture, electrical schematics, mechanical design, 3D wire harness, code generation, system traceability, co-simulation, hardware in the loop simulation, multiphysics simulation, robotic simulation, manufacturing assembly. Each of those disciplines don't go deeper, so this is not the point to explain how you would design this system, but to explain how all the disciplines connect together and interact with each other through baseline management, through traceability, through change, and through other use cases like even AI, how it would enhance, and incorporate this system architecture. And the goal is actually to make this model and this system be rapidly updated, show this return of investment as maybe one of the main return of investments, the ability to rapidly update your project and propagate the change through all the life cycle and deliver the product much, much faster once you already have the integrated models. Also, the goal of the project is, for a few reasons, is to demonstrate technologies, modern state-of-the-art technologies and integrated especially, and also to provide this material for the education purposes, for the business industry, and also for specifically for the universities to adopt for digital engineering curriculum. Here you see full engineering life cycle. It's engineering V, right? We start with the stakeholder needs. We do the system context analysis. We do the functional analysis, understand what user wants from the system. When we go to the solution architecture, optimal solution architecture, actually before system requirements. And then implementation requirements goes to the design, mechanical, electrical design. We specify, concentrate here on the wire harness design. And then manufacturing, and then testing. So testing of the electrical side with, you see, multi-physics simulation, testing of the geometry, and with robotic simulation. Simulating and testing all at once, exercising new scenarios, and operational tracking of the system and comparing real system to the virtual system. As you see here, traceability is gluing everything, first of all, just for the baseline management, right? So we don't want that those models would be disintegrated just because someone updated one and does not know what is impacting that update. But also the change impact of the single element can be tracked if you have element-to-element traceability. Because of the models used here, we can achieve that. From the solution architecture side, here you see capabilities delivered by this example, like co-simulation, hardware-in-the-loop simulation, 3D wire harness design, the requirements management, and then apps like a CATIA Magic, 3D experience platform, in co-simulation environment, again, the same CATIA Magic with simulation toolkit, 3D experience platform with Delmia robot virtual commissioning, the MOLA for physics simulation. Based on multi-physics simulation, you see, you pick this and you get behavior modeling, system simulation design, the MOLA, you see here, and you get the apps which enables that capability. So if you care about some capabilities, but you don't care about other capabilities, you can just pick and choose, this project is available, and you can even filter based on the legends. This internal block diagram here is more detailed list of the software products required for full digital engineering environment based on this example. But it's not all or nothing. Now, when we go through this project, we organized everything in an academic way that you would get information, not academic way, but it's actually kind of like a structured way that you would get information, what app is used, what is the goal of this step, what you do in this step of system engineering lifecycle, what's the impact by system engineering for the step, and how do you do it? Short demonstration, a very short demonstration, sometimes few seconds, but that would be like almost every slide. So it gives you kind of like immediate feel, what's happening. And talking about specific this project and process, we are using Magic Grid for the system engineering to transition from stakeholder needs to the implementation requirements for the design through the stakeholder needs conversion to the model for the user needs analysis, stakeholder needs analysis, transitioning to system requirements, and optimal solution architecture. So here we have requirements. Those requirements can be synchronized from 3D experience platform, from other requirement management tools like JAMA, DOORS. Here we have Data Hub. And this step is very common because requirements exist as a precondition and as a result of system engineering. And they tightly integrate with system models. So here we have that demonstrated with the native requirement management tool in 3D experience platform. But again, we can manage requirements also with SysML, especially you want to do that if you just do the system model side and then later deliver requirements, and then you don't need those requirements be accessible by the rest of the organization outside of SysML. Here we have system context analysis. It is a very important step because we define system boundaries, we define high-level interfaces, But also here you see that part of system context is also virtual twin, is digital engineering environment where we have all those models which combined together called virtual twin, when we have models which are resulted in the final product, and that enables us rapid change. Those are like system model requirements, 3D CAD, and operational models, and so on. And here we see use cases, and those use cases actually include configuration, program, change. So that's the core difference between the majority of the systems which we see here. If we specifically go to the robotics, right, we would see that majority of systems are one of the kind. They are not designed to be configurable, and they don't have that full digital thread. If you don't have full digital thread, you can change at the end, but that is very heavy on engineering. With this project, we demonstrate that you can actually do that very fast, and because you already invested in the models, you know your model limitations, and you can introduce new configurations, new use cases quickly, and have new products delivered based on your product line quickly. So here we see logical architecture. Again, we apply the legends, which allows us to maintain this view up to date without a big effort, because we just want to have single diagram, and we maintain that single diagram. But when we go to present and communicate with other teams and team in general, we can filter based on selected interfaces, based on type, and that is enabled by automatically extracted legends. And that gives us ability to work on single view at the same time maintaining that single view, which was not before available. What's the difference between solution architecture and logical architecture? In logical architecture, all the blocks, parts in this case, represents the accumulated representation of the typical functions. Like, for example, control functions would be in controller, right? But that's not actual controller. For example, screen. So the visualization functions would be in the screen, right? But we don't specify what screen, how it will look like. Maybe it would be external to this device at all. Right? When we go to solution architecture, now you specify, you see screen is Arduino, controller is Arduino controller, and then screen is OLED. But we need to be also careful here, because every time you specify something, it is a requirement for the design. And maybe we want to have that requirement for the design, maybe not. Sometimes we are not comfortable to specify the requirement because we are not experts in that specific field. In that case, this view, because it is single solution architecture, optimal in our case already, we might invite experts to contribute to it in order to have best solution architecture for our system. Now we transition to the 3D CAD and mechanical design. And CAD is kind of same as SysML, is precondition for many things, because you can do analysis on top, you can do deliverables of your system for manufacturing and for other reasons, visualization, right? Here you see CATIA CAD used. This robot was created from scratch in CATIA. And then we go to the electrical design, and we start doing schematics using libraries. So here you see the schematics, controller, 5 servo motors, even gauges already here, connectors. And then we allocate electrical parts to 3D in order to perform so-called electrifying CAD. This is a big deal, because then you have full understanding where your wires are going. You can just go through the schematics and you see where the signals are going. It's not yet wires, right? But just as signals, because you see here just pointing from this connector to this connector, right? Also, you can achieve that once you update the parameterized CAD, and those parameters can come in from SysML model, you get automatically reconnected everything. So you will no longer depend on the actual design here in the CAD, you actually have ability to change parameters and design will change automatically. So next step is designing the wire harness. So this is based on those connectors and based on the intermediate connections here. Those wire harness are created automatically. You can adjust them, but it's based on the parameters. Pretty much they are recalculated. So that gives us ability to have parameterized update of the model later on and save a lot of time. So how it works, for example, we bend this robot based on joints, and this, when CAD is created, it's actually created, based on constraints. It's not that we assemble everything, just visually putting things together, but actually we create constraints, and that allows us to move this robot based on joints, and later even automate it, in a couple of clicks that it would move automatically based on those joints and constraints. But that also gives us ability to recalculate wire harness, change the characteristics of the parts, and everything stays the same, right? So it's not like one of 5 variants, right? Here is like you can just change parameters, whatever you want, and that will still be useful. But then you need to run analysis to identify actually is it running as it should be running. So we'll talk about analysis later on. So here, next step for wire harness design, we transition from 3D robot to separated wire harness to flattened wire harness, and then to the drawing, which is delivered for the manufacturing. And this drawing, again, is updated once you change the parameters in the initial arm. That could come from SysML model. So here we see a short video how that wire harness is designed, is manufacturing. So pretty much you receive the drawing, which you saw here, which is digitally made, right? If it is updated, it is just a couple of clicks, you get updated drawing, and then you put on the table. And also you can have it as a specification, depending, is it algorithmic, is it like a real, size drawing? And the wire harness gets manufacturing based on that. You pretty much step-by-step lay the wires based on specification like that, and manufacture it. Now we'll go to the digital thread and traceability and baseline management. So for that, we used file-based combination with automated Power BI, so-called Power BI, when you use, for example, CATIA Magic, Cameo, and you commit project directly to 3D Experience platform. You can do file-based, which would be a manual work to add that file, completely fine, right? But you can also automate that. And also we use system traceability app, which allows, doesn't matter where the data is coming. Is it Simulink data? Is it, CATIA Magic data coming from Power BI or file-based? Allows us to link and trace the data. So here you see the traceability. So in our context, let's say we select controller in 3D CAD, right? And then we say, show me everywhere else it is available. So it will show you that it is available in schematics. There is solution architecture, there is logical architecture, there is requirements, system requirements, what the stakeholder needs, everything will be displayed with the visualization, also with the part of the project where it came from. The digital thread is available. Some of those links are manually created between CAD and SysML model, manually created between CAD and electrical, extracted between requirements and SysML, extracted because we had data hub synchronizing. Here we had electrifying CAD, so those links are reused. Also SysML between problem domain solution architecture, automatically extracted. We don't need to update those links. Just the ones between, in our project, the ones between CAD and electrical and SysML. To SysML pretty much, because some of those electrical components goes directly to SysML. So here we see short demonstration how it looks like. So we have custom views added I mean, custom because we can choose, what kind of viewers we want to add. The same system traceability app is used here. Here we have CAD viewer. And then once you specify what model should cover what, as you can see here, we are following kind of magic grid, and then we follow engineering V. And then you select in the full traceability, anything like servo motor, you see here servo motor here and servo motor in the schematics, right? In this case, it's connector of the servo motor, right? So you see here, again, here you see in schematics, and we see here linked into the 3D CAD. And then also we see port in SysML in the solution architecture. Traceability has two views. One view is everything, like here. So whatever you select, you get actually more than two views. Like this view, for example, also is like overall picture. But there are two major views in the detailed traceability. One view is that you see what is around your selection, and then another view is impact view. Then you see through all the digital thread was impacted and only that impacted piece. That's like kind of filtering a lot. Then what next after traceability? So you can actually navigate through the model, demonstrate it, see impact, and that gives ability to identify what will be required to change if there's issues. So how to manage those issues? In the traceability view, you can create nodes, like say like, oh, this element I want to change, right? Like I want to make longer arm reach, right? Okay. Longer arm reach. So from that node, I can create issue. That issue automatically or manually dragging elements can include what model elements will be affected, like CAD, SysML elements, electrical elements, requirements. And then I can create sub-issues, say like update the 3D CAD, update the electrical design, update the system architecture. And those issues can be assigned for people. We get notifications. And even because we are following formal process, if the design is already frozen, right, we convert this issue to the change request, change action, which is actually after the change in the model, is revising that model and introducing new revision of the models, like baseline and Teamwork Cloud, right? So this would be formal process, but if informally, this change would be just like that. You see, I double click on the arm length, arm, shoulder, or whatever, and say like change me to the what needed. Click refresh, and everything gets recalculated. Wire harness gets recalculated. 3D CAD gets recalculated. Drawing gets recalculated, which results in the different number here of the length of the wire harness. That's the speed of update. It's actually, as you can see here, minutes from the parametric side. From the workflow side, it's longer because it is approvals and it's revision and other things, But from the models side, integrated model side, to do it, you no longer need, everyone on board to exercise what-if scenarios. But you might see the missing piece. Actually, we can change the length and we can go with the new characteristics, but how we will check virtually that it works. So we need to check the motors that they are powerful enough, and we need to check space in which exists this robot, that it will reach the required target. It's because of the requirement is the long arm reach, and it will not collide based on its path with other robots in that space. So that's what we do with the testing, and we'll demonstrate how do we do it. So for the motors testing, we use multi-physics simulation with Daimler. Here you see robotic arm sample. We have the joints, and every motor can have alternatives based on libraries. We can choose more powerful, less powerful, and run through scenarios, and we set the target of the robot, and then we get how fast it will reach the target. Will it reach the target at all? Will it be powerful enough to lift the longer arm? And we integrate with CATIA Magic, so we can achieve that requirements verification which exist in CATIA Magic based on scenarios manually automatically executed and getting back characteristics of the simulation from the model. As you can see here, we are tracking voltage of every joint real time. When we execute through the scenarios. Those scenarios can be treated as a test cases or as a use case based scenarios. We're just running and demonstrating, that it does this, and we get results. For integration, we use functional mockup interface standard FMU, which allows us to integrate models through shared memory, through serial, through TCP/IP, UDP. We use FMU communication over UDP out of the box interface. You can just generate that interface and get the results of fast integration, fast, stable, reliable integration. Now for the collisions with the rest of the factory floor, the robot is not isolated. It is in some cell, right? So it does the work, right? And even in the cell, it needs to go through optimal path. If we'll increase the length of the arm, we need to know that it will deliver the right results, that it will have a good reach, right reach. And we can achieve that with the robotic simulation. We take this CAD. First of all, we enable the robotic simulation. That takes like an hour from empty CAD, to achieve that. Took us 1 hour. So it is very tightly integrated, same CAD based, right? And also connection to CATIA Magic to run through the simulation in order to achieve the scenario verification, same as with physics simulation. Also using FMU, functional mockup interface standard, also same way integrating because the tool supports functional mockup interface. So we use those powerful robotic simulation applications like virtual robot commissioning app, which allows you to do more ergonomics, robot logic development, kinematics, motion planning, collision detection, virtual commissioning, offline programming. And here you can see video how this robot would be tested and programmed to deliver this ball from one side to another side. So we first of all analyze what's the reach of this robotic arm based on CAD and based on the joints. So if we increase the size of the shoulder, so we would have different reach. So we would rerun this analysis. We would get a new path likely, or we would check that path is correct. Because when it was originally here programmed, we saw that path was had some issues when we move in the fastest way, we collide with some obstacles. Here we see this path. And this application, even it is dedicated for robot programming, once we integrate with CATIA Magic, we can run simulation directly through CATIA Magic and do requirements verification. So this could run, this program from this application, robotic simulation, and give feedback loop for requirements verification to SysML, or it can run from SysML scenarios and simulate here a robot. It actually bi-directional. It gives very good performance results, very fast to use and integrate, very stable, gives fast simulation on multi-joint robots. In general, CAD animation, that's achieved, to the scaled version. In most cases, if you deal with the 3D, you would expect delays and need for the powerful PCs. So you need powerful PC, but you can get like big simulations running, and again, the integration with CATIA Magic through FMI gives that intrusive method, of co-simulation. So as a result, we achieve this co-simulation environment where we connect the hardware, as you can see, through Internet of Things protocol MQTT. We have open library by CATIA Magic provided, which you can use. It is we are providing it for no cost from community. You can get that very simple library. Very simple but very powerful library to control Internet of Things devices, listen for those devices, publish and subscribe. So we are using that to control hardware. Then we are using functional mockup interface generated from Daimola to interactive physics simulation Daimola and with robotic simulation. This interface is parametric based, so it does not require tight integration and is not required to finish simulation to do something. It is actually working live, interchanging properties and allowing you to have that feedback loop immediately. So here you see result when we run the robot, it's running from CATIA Magic based on this scenario. You can do manually, you can do automatically based on state machine activity diagrams and whatnot. And SysML is very powerful simulation, right? And then here we are running hardware, and also in the top screen, we are running physics simulation in Daimola on the 3D Experience platform or standalone. Here is on the Experience platform. It's called Behavior Modeling app. Standalone would be Daimola and tracking characteristics. Here you see same sample running, but now we are running virtual robot commissioning in the top right corner. All of those apps can run together, we just were like short on screens, But actually in this video, we see that all of them are running together. Daimola is running here, you see on the right side. CATIA Magic is running on the left side through web simulation interface, right? We are just running simulation behind the scene and exposing web interface for the UI of CATIA Magic. And this is enabled by this architecture, which is very modular, expand to many tools, scale easily because it does not overcrowd with the processing power each tool, right? They just do right thing, communicate through FMU, functional mockup units, and currently a functional mockup interface is supported by 230 tools. So you can imagine what's the potential of this method. Now, from application side, once you're in operational scenario, you can actually send sensors data from your factory, from your robots, back to the virtual twin, virtual environment, with your robots running virtually, and check that they are performing exactly as needed. Are they in limits? You can have a virtual dashboard monitoring that, And that's not like always. So you can just say, oh, I want to check. So you just power your virtual environment and it connects through Internet of Things, through FMU, from other standards, and gives you back results of the execution of operational robots compared to the requirements and virtual robots. Now, if you want to exercise this scenario, this has never been easier. We provide you with the models, reach to us, will help you to deploy them. We organized already maybe 7 workshops this year, and we'll have another 5 or 7 till end of the year. We will go like in 4 hours or full day, step by step through this environment. But precondition is always for hardware, and I think hardware is very important to buy that hardware. So you can buy it like, I think it's not our product, right? So you can achieve that hardware piece by assembling it in 1 hour or so. It's currently costs like $60. I don't mention here, it comes with special batteries. So take a look, that you also need those batteries. And this is like, like there are a lot of robotic arms and There will be much more in the near future, smart robots and so, but this one is not bad. It's actually working out of the box, has some spare parts, and it will work with all those models which you saw. So you would be able to adopt and change it. So it's not closed environment, right? You can change it. Talking about interesting use cases. So for example, because this robotic arm has a servo motors, they don't provide position. They are listening for position. So we are sending from CATIA Magic, like from 0 to 180 position of each servo motor, deliberately very straightforward communication and control, but they don't give you actual position where they are. So we thought, okay, we need some sensors, and definitely with sensors you can achieve many things. So we thought, okay, what's the best sensor? Would be camera. So we put camera, small camera here on the robotic arm, and what it could do, it could, for example, track what's happening around. So that's what we enabled. We enabled AI vision. So it tracks with the camera what's happening around, can recognize objects. And then when the object is recognized, it can track the position of objects. So because it has multiple joints, so it can, change the orientation, track the object. And also we can enable a process. So for example, state-based process that whatever is happening around would follow the predefined process. If not, then based on vision, we don't transition to the next step. So in our case is building this house, and every state exit criteria is based on AI vision telling us that we passed that criteria. If not, it will tell us something wrong or repeat the step. And that's like unlimited possibilities here. So let's see how it works.
Factory mode.
Factory mode.
So now it's looking at those 3D objects.
Let's build the house.
And now once we start state machine, it queries the
Start house from blue foundation.
AI in order to
Blue.
check
Good.
the image
Second
and
floor
see
shall
that
be green.
it sees that in the
Blue.
image. So it's almost every
Blue.
every state has like
Second floor shall be
find
green.
that object, find the sequence,
Yellow.
find the sequence like a blue, green, yellow.
Second
So
floor
first
shall be
state
green.
was find that blue is on the
Green.
ground. The second was find
Good.
that
Top shall be
blue
yellow.
and green is on top.
Green.
And the last
Top
one
shall be yellow.
is full house.
Well done.
If it finds, then it gives feedback loop. Yes, I found, true or false, right? So then in that case, you can have like single query of AI, but at the same time, it can be like reused quite universally. So this is one way it applies, in context of AI, but AI is same like traceability, same like cost simulation, gives you additional level of the value of the models. It's like enormous increase multiplier of the models, because now you have all the physics, you have the reach, and now you have real-time sensors loop, which can adjust your actual product. So what's the current plans? So expand the adoption. We already enabled 50 users with this data set. That includes educational organizations. We have team which builds the educational material for the training. End of the year, we plan to have it, and it will be like 10 modules. And also we are enabling universities, enabling clients. We deliver workshops. We are expanding this ecosystem to more products. We are delivering new use cases like AI vision, right? We are delivering also new configurations of the sample, and especially that on requirements verification, that we would have feedback loop from every tool which virtually connected, that it would deliver right requirements verification. Every tool is different. We can't achieve everything with single environment, right? With single tool, but we can have environment. And because that interface like FMI is scalable, very scalable, we can have requirements, multiple types of requirements in CATIA Magic, and get result of virtual verification based on multiphysics, based on 3D geometry, based on other criteria from dedicated tools giving back results running through the scenarios of requirement verification. So that's pretty much the main story and the main goal, that we would demonstrate how that is achieved, and that very easily transfers to the real projects because the same technologies can scale. And all this material can be found in the community, and we can communicate through community if you will want us to help you adopt this material, this project. Please reach through the community. The main community is CATIA MBSE Cyber Systems community. Join it if you are not joined. You will find this Robotic Arm project there. And also you will find 2 more posts on related projects which are using in nuclear energy this approach, where we definitely can go in and do that physically in some place, but robots can test virtually scenarios and then can do physically later on. Again, you can find that in the community, so please visit them, and thank you, and let's keep in touch. Here you can scan this QR code, and it would reach you to the CATIA, to MBSE Cyber Systems community, where you will find this Robotic Arm project description with some of the models available. Some of the models requires you to reach to us, and we'll provide them because there are some kind of updates and so on. But all of this project is pretty much open for the community.
Okay, so thanks a lot, Sauliau, for your presentation, for really lots of knowledge, lots of experience you experienced during this project. And I have one question for you. During the presentation, you mentioned virtual twin, digital twin. So can you tell us what is the difference between virtual twin and digital twin?
Okay, so what's the difference? So digital twin we understand as a last step when we have a system as is virtually defined, and we have operational characteristics coming from the actual system, and then allowing to compare, to update, to improve that system. But because we just limit to digital twin, so it's like digital, right? It's like copy of the real system, right? This is not like a really system engineering, because it's lacking of the understanding why the decisions were made. So we need all the models, how this was made, and all of them can be integrated more closely or like tightly on or less. Like, for example, traceability would be least tightly integrated, but it still would give us ability to update and see impact of every decision. Because if we decide to make a longer arm reach, this might affect everything, including materials, including the type of the motors and everything. And that requires to rethink, was that the purpose? Like the packaging size, will it be still big enough, still small enough to satisfy all those requirements? And many of them are like at the high level, at user level, right? Came in at the beginning. So that's the difference. Full models for the engineering would be virtual twin, and digital twin just the last step, copy of the system.
Okay, thanks a lot. So I don't see any questions in the chat. However, I have the other question which I received up front. What value model-based solution add to digital engineering?
So model-based gives actually an enabler for the integrations. If and understanding what's happening in the digital world. Because visualization is one thing, you can visualize things in the dashboards and so on, but what's behind the hood, you don't know until you have transparent project structure, transparent data. And that's the model base. So you can, for example, align connections, what parameters will be integrated, right? And at what moment, right? So this model gives you ability to integrate with other model. And that's why, we are so much reusing, SysML and multiple integrations, because it enables the ecosystem from integration side. Same like CAD, because it is model, it enables to reuse it, for the analysis, for manufacturing. It can be parameterized, can be updated in seconds. If it would not be model-based, if it would be just like code somewhere hidden, it would be always that engineer who wrote that code, to change. And we don't want that. We actually try to increase the abstraction level from the deep understanding of the all nuts and bolts, to the ability to manipulate by the one who wants to achieve the results based on the availability of the models.
Okay. So thanks a lot, and thanks for those who were together with us. Just a short reminder that all the replay will be placed on MBSE Cyber Systems community, also on YouTube and on LinkedIn as well, just for you to know that Solus is one of the greatest contributor to the community. And if you have questions and want to ask him about this topic or other, please ask your questions and Solus will answer. So again, thanks Solo for your time, and thanks everyone who were together with us. Meet you in other CATIA Systems Masterclass. And now I'm saying you goodbye.
Bye. Thank you, Gatana.